This is the way Bayes' theorem is written in your textbook in RADA, and it's useful as always to get in the habit of seeing the basic pattern, the basic structure, because the way that they write it's in terms of the choice of H and E is arbitrary. We could use A and B, we could use X and Y if we want. As long as we understand they were events. But the choice of H and E is, although arbitrary, is useful or is indicative of the overall goal of thinking in terms of hypotheses or claims on one hand and evidence on the other, right? Because the way this is set up is the way we are usually going to be facing a problem in a scientific situation or a legal claim or um, a medical risk assessment, right? Probability of hypothesis given evidence, right? In light of the evidence, once we know certain evidence, how do we assess or express, communicate the uncertainty about the hypothesis? As we get new evidence, how does that help us refine our beliefs about the hypothesis in question, the claim in question? And it's a very simple and elegant theorem that is actually just a consequence of a couple of simple rules we already have encountered. And just to read through what this says is probability of the hypothesis given evidence is equal to probability of the evidence given the hypothesis times probability of the hypothesis divided by probability of evidence. And again, this works with any events, and the key the key point here is that often we know one direction. We know not the band, but the facts about how likely certain evidence would be if the hypothesis in question were true, right? And what we want is the inverse of that. We want to flip the conditional, and we have that prosecutor's fallacy of flipped conditionals or inverted conditionals, where uh, we're we have to acknowledge the fact that probability of E given H is not the same thing as probability of H given E, and quite in some circumstances they're quite different. And so let's actually start with the rule in basic terms of just two events, E and F, right? So again, just getting used to seeing whatever, because this is going to matter for an application, whatever is on one side of the conditional sign, what side of the other, how do we apply Bayes' theorem? And so what you see here, probability of event E, given we know event F happened, we already have seen this was from our, explaining the observation, and then I believe it was axiom 4, the conditional probability. Probability of E given F is equal to the probability of E and F, probability of them both occurring, probability of the intersection of the events divided by the probability of F, that which we're conditioning on. We're constraining our attention to what we already know. That's the denominator. We're reducing our sample space to just the part where F occurs and saying, okay, under the circumstances, what's the probability that both of them occur, E and F, once we already know that F occurs, right? So notice that the E intersect F, it doesn't matter which order you write it in. You could write it as F intersect E, the probability of both happening. That intersection is commutative. And we have the intersection, the probability of F and E is equal to the probability of F given E times the probability of E. Why do we know that? Well, we have our general multiplication rule, which we've encountered already on one of our sort of key facts slides. And so we can replace probability of F and E, or F intersect E, with that conditional, right? It's like, again, going back to the example I use over and over again in class, if these two events were event it's raining and event my socks get wet, this would be like saying, okay, well, the probability of rain and socks wet is equal to the probability of socks wet given rain times probability of rain, right? And then still divided by probability of f. So why is this incredibly useful? All we've really done, I mean, this is barely even a theorem. It's barely even, I mean, essentially that's a proof. I'm not making you do proofs, but we just used a couple of facts. It's rewriting probability of conditional in one direction using the probability of the conditional in the other direction, right? So if we know these other pieces, we can flip, we can get the conditional that we don't have that we want, right? We may know one direction of conditioning and we want to know the other. There's this one other key complexity, which is that sometimes we won't have probability of f exactly. We'll have it in pieces, right? And so I want to point out, let's just quickly do a little Venn diagram here. If I've got my space of the things that can happen, and let's say that I have divided into a partition of mutually exhaustive and mutually exclusive parts of that sample space where where E is the case on one side and E complement not E is the case on the other side. Well, oops, sorry, that should have been E complement, not E squared. Silly me. All right, so not E. And let's do in blue, let's imagine that we've got this other event F in here. Notice that, so if we have, what's on one side of the red squiggled line, we've got E intersect F, right? It's the part of the F that's overlapping the event E. So again, just I didn't write it down, but F is that entire uh, lima bean or peanut. And then on the other side of the line, I've got the event E complement intersect F. So of course, if we had those two pieces, if we have the probability of E intersect F and we have the probability of E complemented intersect F, or I put it in the opposite direction, probability of F intersect E, probability F intersect complement E, then the probability of F is just the sum of those two, right? So I can, this is called the law of total probability, right? That I can piece together the probability of an event if I have the probability of its intersection with exhaustive mutually exclusive pieces of the entire sample space. It's a little bit daunting, and that's looking at this, right? Because what I've done is I've rewritten probability of F intersect E using this rule that we've used over and over again, multiplication, probability of F given E times probability of E. And I've rewritten probability of F intersect E complement using the same rule, probability of F given E complement, probability of E complement. You can think of this in a sense as sort of like a weighted average, right? So probability of F is probability of F when E is true, weighted by the probability that it's true, plus the probability that F occurs when E doesn't occur, when E is not true, weighted by the probability that it's not true. And either E is happening or not E is happening. And so we're covering all our bases and piecing together the total probability of F. So, that is, if you're encountering this for the first time or the second time, probably very confusing. And it's one of the reasons that in a separate video, I do Bayes' rule through a tree diagram. It's easier to see, okay, well, we're in this situation where, say, E occurred, let's focus on, or the probability that F occurred, let's look at the parts of the tree where that's true and put that in our denominator. Um, but it's worth at least encountering this, and I'm going to use this in rerunning the example that I did with the tree method, but this time using this formula. Here, let's just notice that that denominator probability of f can be rewritten using the law of total probability. If we only that's if we only have the pieces. If we don't have probability of f, but we've got probability of f given e, we've got probability of e, and so on. We're going to see that in the example with the support for the COVID relief bill. Okay. So I'm going to pause this now and then do a second part, rerunning the example of Massachusetts registered Republicans and Democrats and their support for COVID relief.